Okay, we're going to continue our lesson on 10.4 right now, which is solving trig equations. And let's try, just like we did in the last video, we're going to start with some just basic equations and review, what we do to isolate the variable here. So let's solve for a. I'll start by adding 9. I'll divide both sides by 3. And the key part here that I wanted us to notice is my next step is to take the square root of both sides. And remember, when we do that, we have to introduce a plus or minus along with our square root. So we get a equals plus or minus root 3. And those are my two solutions. Okay, we're going to see a problem very similar to this in a moment, only instead of a, it'll be a trig function. What about a squared minus 3a equals 0? How would I solve that? To solve this equation, I need to start with my most basic kind of factoring. It's the first kind of factoring I always check for, GCF. What is the greatest common factor of my two terms? It's a. So I factor out an a, and I'm left with a minus 3. Now, to finish solving, I set each factor equal to 0 separately and solve. So a equals 0, and a minus 3 equals 0. I got to finish solving this one by adding 3 to both sides. And my two solutions are a equals 0 and a equals 3. Now we're going to see a problem in a moment where instead of the two factors being a and a, they're going to be two different trig functions. But I just wanted to remind us of our plus or minus and of our greatest common factor factoring to solve an equation. So let's try a trig equation now. And here we're looking for the general solution of the equation. So we're going to have that n, where n is an integer in our answer. And let's solve it. This is just like 3a squared minus 9, only it's 3 tangent x squared minus 9. I'll add 9 to both sides. Remember, tangent squared x is just a notation that means tangent of x, quantity squared. Okay? It just means the whole thing is squared. It's just kind of a special way of writing that. Divide both sides by 3. And my next step, just like when I solved for a, my next step will be to take the square root of both sides and to introduce a plus or minus along with it. Tangent of x equals plus or minus root 3. Now, this part's hard, okay? First of all, I've got to figure out which quadrants could this unknown angle be in. Well, students take calculus. Look at this. Whatever angle this is, tangent of that angle is either positive or negative. Well, tangent is positive here and here, and it's negative here and here. That means I'm going to have a solution in every quadrant. Positive solutions here and negative solutions here. I've got the difficult task now of figuring out what angle is going to have a tangent of plus or minus root 3. Now, remember, when we're dealing with 45-degree angles, tangents of these problems, y over x, because the legs are equal in length, tangent is always 1. So it's not going to come from a 45, 45, 90 right triangle. Instead, it's going to come from a 30, 60, 90 right triangle. Okay? Tangent is y over x. So one thing we could do is we could say, I'm not going to try to draw this either as the 60 or the 30. I'll just draw it kind of as a nondescript angle. Tangent is y, root 3, over x, 1. Now, if this is 1 and this is root 3, what angle is this? This would have to be a 60-degree angle, right? And what would the hypotenuse be, out of curiosity? 1, root 3. The hypotenuse would be twice the shorter side, so 2. So I know that it's a 60-degree central angle that gives me tangent of root 3. If I wanted to list this point, it's 1 comma, get out of the way. It's 1 comma root 3. Tangent is y over x, and so tangent of 60 degrees, and remember we're going to be giving our answer in radians, so 60 degrees is pi over 3. Tangent of pi over 3 is y over x, that's root 3. Okay? Now because I decided that there's going to be a solution in each of my 4 quadrants, I'm going to go ahead and draw that 60-degree angle. And here, since I know it's 60, I'll go ahead and draw it more to scale. In each of my 4 quadrants, there's 1, and there's 1. No, this is 60, 60, and 60 degrees. These are all going to have tangent values equal to plus or minus root 3. And let's check. Now keep in mind, the way I drew this triangle, first of all, wasn't to scale. That looks more like 45, even though we decided it was 60. And also, this isn't in the unit circle. We don't have to be in the unit circle. It's just the unit circle is sometimes more convenient, but mostly when we're doing sine and cosine. This is the 2 unit circle because its radius is 2. So we'll stick with that. 2, 1, root 3. This is 1. So this would be root 3. This is 1. So this would be root 3. Radius of 2. So let's label these points. This is negative 1 comma root 3. This is negative 1 comma negative root 3. And this is 1 comma negative root 3. Now, we actually don't need to be doing this work right now. I'm more just trying to show you that these are in fact my solutions. So negative 1 comma root 3, if I did tangent, y over x would give me negative root 3. Negative 1 comma negative root 3, y over x, negative root 3 over negative 1 would give me positive root 3. And y over x here, negative root 3 over 1 would give me negative root 3. So all of these angles work. Now I'm going to try to redraw these 4 angles a little bit more to scale, and I'll do it right here. These are all the angles with a 60-degree central angle. And I need to figure out, if these are all 60, what are these angles in radians? This one's pi over 3, 2 pi over 3, 4 pi over 3, and 6, wait a minute, 1 pi over 3, 2 pi over 3, 5 pi over 3. Careful. Okay, 5 pi over 3. 2 pi over 3 and 4 pi over 3 we recognized from our problem in the last video, actually. So, tangent of x equals plus or minus root 3 over 3, is all 4 of these angles if all I'm looking for is the solutions between 0 and 2 pi. There'd be 4 solutions. But I'm not looking for that. I'm looking for my general solution. And so instead, I'm going to need to say pi over 3 plus maybe 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n, where n is an integer, right? And that would give me angles that were coterminal with this, angles that were coterminal with this, then with this, then with this. But notice that these 2 angles are exactly 180 degrees, or pi, apart from each other. So instead of going around a full 2 pi to get to the next solution, I can go around exactly pi. And then if I add another integer multiple of pi, I get back to another solution. If I add another integer multiple of pi, I get to another solution. So for tangent, only for tangent, because the solutions are spaced evenly apart, instead of saying all 4 of them plus 2 pi n, I can say this one plus 1 pi n. And that gives me all of these solutions and all of these solutions. I can also say 2 pi over 3 plus 1 pi n, and that gives me these solutions, and pi away from that, and pi away from that, and pi away from that. So we can see that 4 pi over 3 and 5 pi over 3 are specific instances of pi over 3 plus pi n, and 2 pi over 3 plus pi n. These are my general solutions. Let's do one more example. So, okay, sine x cosine x minus 3 cosine x equals 0. This is a little bit like that second problem we did here. I'm going to look for my GCF to start with. I see that cosine is in both terms, and so I can start by factoring that out. I'm left with sine in the first term and 3 in the second term. And then I set each factor equal to 0 separately and solve. So I've solved for each of my trig functions. That's always my first step. Now I've got to ask myself, for what values of x, for what angles, is cosine of that angle equal to 0? And for what angles is sine of that angle equal to 3? And because we're doing sine and cosine, I do think it's easier if we think of the unit circle with a radius of 1. I love the unit circle. Did you know that? I do. Okay, let's start with cosine x equals 0. Remember, cosine is the x value on the unit circle. For what values, for what angles is the x value 0? Here's one, an x value of 0. That angle is pi over 2. And here's one with an x value of 0. That angle is 3 pi over 2. So the angles that work are pi over 2 and 3 pi over 2. Now, if I were to just write that, I would be finding only the solutions between 0 and 2 pi. Because even though pi over 2 and 3 pi over 2 are solutions, so is 5 pi over 2 and 7 pi over 2 and 9 pi over 2. And for that matter, negative pi over 2 and negative 3 pi over 2 and so on. So to give my general solution, I want to say pi over 2 plus 2 pi n and 3 pi over 2 plus 2 pi n. But you'll notice, just like the tangent function, these two solutions for cosine are exactly pi apart from each other. So I can specify both of these answers by just saying pi over 2 plus any integer multiple of pi. If pi is 1, if n is 1 here, then I'm saying one of my answers should be pi over 2 plus pi. And here I am, pi over 2 plus pi brings me to 3 pi over 2. So there's no reason for me to specify that again separately. Okay, there's part of my general solution. Now let's solve this one, sine of x equals 3. So let's look on our unit circle. Remember, sine is the y value. Where would the y value be equal to 3? Well, up here the y value is equal to 1. That's not big enough. And as soon as I keep going, the y value is getting smaller